Welcome. In this session, we'll explore a non-convex optimization problem. Here, our objective will be convex. It'll be a linear objective function, and we'll have a non-convex constraint. And what we want to do is continue to explore what the Lagrange multipliers look like when both of these are satisfied. So let's continue with our example. So let's consider this. Let's suppose that what we want to do is we want to find a stationary point that is a minimizer over all of the vectors in the vector space of a third objective function. And what we'll have for this is, let's set this third objective function to be linear. Let's suppose that it's the one form 1, 1 times the argument. And we can see immediately that if this was an unconstrained optimization problem, this would be something down at negative infinity for each of the entries of that W. So as an unconstrained optimization problem, the answer is it's going to point way, way off in minus infinity. And what we'll do is we'll add a property function, and this property function will be a quadratic function. So it'll be, let's pick a different quadratic than we had before. And let's make this the first entry minus 1 squared, and then we'll subtract the second entry and we'll add 1. And what we'll do here is we'll require that at this stationary point, that when we evaluate this third property, we get 0. So this has a linear objective function and a non-convex constraint. So when we go to draw this, what's that going to look like? Well, now we're going to have to think. So let's write this down as here's our W1 and here's our W2. And I can identify that this one is going to have, this will be a quadratic function. And if I switch to a different color here, that will look something like this. I'm not sure exactly where it's going to be, but it'll be a quadratic that looks something like that. And now, what are the level curves of this? Well, if I pick a 0 level curve, then that would just be a single point. But if I've got some level curve of this, what these are going to look like is these will be lines. They'll be parallel lines, and the normal vector for them will be the transpose of 1, 1. So the normal vector will point like that. And that means that these will be lines that look like this. So our level curve for this is a bunch of lines. And we can see, as before, that there is some level at which the level curve of the objective, which is this line, does not intersect the curve of the property function, which is another way to say that is there is no point on this level curve that satisfies this constraint. And then if I pick a different level, then there are 2 points that are on the level curve of this objective and that satisfy this constraint. So as before, let's compute the gradients. So here, the gradient of function 3 will just be, you remember how to find the gradient of a linear form, right? That's just the one form. So that'll just be 1, 1. And then the gradient of the property will be, the first entry is the derivative of the property with respect to W1. So that will be 2 times W1 minus 2. And I'll put a comma so that we're very clear. And then the second entry of the gradient will be the derivative of the property with respect to W2. So that will just be minus 1. And now the question is, what is the value, what is the argument such that the level curve of the function and the level curve of the property intersect. Now let's do the computations. What we'll do is, as before, we'll increase the level until the level curve of the objective just touches our constraint parabola, and we'll find that this happens at this stationary point for problem number 3, which has these entries. And this is what we drew before, and now we can see that when we do this computationally, that indeed there are some levels of the objective function that don't intersect the property curve and some that do. And what happens at that single point, at this place where there's a single intersection? When we do the computations, we find that the gradients are once again parallel. In this case, they're opposite to each other, and the multiplier for them is the scalar -1. So now, in these 3 sessions, we've persistently seen that even for non-convex problems, when the level curve of the objective exactly intersects a level curve of the property, that the gradients are parallel and are a scalar multiple of each other.